Welcome to Study Loop.
The presence of resistance in an LRC circuit affects the frequency of oscillation and causes the amplitude of the oscillations to decrease over time. The angular frequency of damped oscillations is given by omega prime, which is equal to the square root of 1 over LC minus R squared over 4L squared, where L is the inductance in the circuit, C the capacitance, and R the resistance. So we can find this angular frequency since we have all these values. So we substitute them in, and this is the square root of 1 over, and L is given as 22 times 10 to the minus 3 henries, so we suppress the units here, multiplied by the capacitance of 15 times 10 to the minus 9, and that's farads, minus R squared over 4L squared, and the resistance is given as 75 ohms, and that's squared, divided by 4, into the inductance again is 22 times 10 to the minus 3 henries squared. And if we do this calculation, we get that omega prime is equal to 5.5 times 10 to the 4 radians per second. And so that we now that we have the angular frequency, we can calculate the frequency f of these oscillations. And f is equal to omega divided by 2 pi. So that's 5.5 times 10 to the 4 radians per second over 2 pi radians. And hence we get the frequency to be 8.76 times 10 to the 3 per second, or hertz. And this is equivalent to 8.76 kilohertz. Next, we want to calculate the time it takes for the amplitude to decrease to 10% of its peak value. So we'll use the equation that the amplitude as a function of time, A, is equal to the peak amplitude A naught times e to the minus r over 2L times t. So we can rearrange this equation and solve for the time t. If we do some mathematics and take the natural log of both sides, we can find t to be minus 2 times L times the natural log of A over A naught, all divided by the resistance R. And again, these values are all known. That's minus 2 times the inductance of 22 times 10 to the minus 3 Henry times the natural log, and A over A naught is 0.1. Since the amplitude drops to 10% of its initial value. The resistance we know is 75 ohms, and hence we get the time for the amplitude to drop to 10% of its initial value to be 1.35 times 10 to the minus 3 seconds, which again is simply 1.35 milliseconds. So finally, we wish to find the resistance at critical damping. And R at critical damping is equal to the square root of 4L divided by C. So we can calculate this value for R. And this is the square root of 4 times L, which is 22 times 10 to the minus 3 Henry, all divided by the capacitance of 15 times 10 to the minus 9 farads. And hence we get a resistance of 2420